The Duesenberg J562 engine was a marvel of early 20th century automotive engineering, powering the legendary Duesenberg Model J. Introduced in 1928, it was an inline 8-cylinder engine with a displacement of 420 cubic inches, 6.9 liters.
Designed by Fred Duesenberg, the engine featured dual overhead camshafts and 4 valves per cylinder, an advanced configuration for its era.
It produced an impressive 265 horsepower, making the Model J one of the most powerful and prestigious cars of its time. The J562 engine's smooth performance, refinement, and durability cemented Duesenberg's reputation for innovation and luxury in American automotive history.
The Juul horizontal steam engine, rated at 10 to 12 horsepower, was a compact yet robust power source widely used in the late 19th and early 20th centuries. Built for reliability and efficiency, it featured a horizontal cylinder design that provided smooth, steady motion while minimizing vibration. This engine was commonly employed in small factories, machine shops, sawmills, and agricultural operations, where moderate but dependable power was required. The Juul engine was admired for its durable construction, ease of operation, and relatively low maintenance compared to larger vertical or more complex steam engines. Its horsepower range made it versatile, capable of running woodworking machinery, pumps, or threshing equipment. Many were mounted on portable skids or wagons, allowing them to be moved between job sites. Engines like the Juul 10 to 12 horsepower played a vital role in the spread of steam power to smaller scale industries, bridging the gap between hand labor and large stationary engines. The steam donkey pull is a modern twist on an old logging tool. Originally, steam donkey engines were built to help loggers drag felled trees from the forest to a stream, road, or railway for milling. Mounted on wooden skids, these portable machines could haul themselves into place, then anchor to a sturdy tree or rock to winch massive logs. In today's tractor pull events, the steam donkey is repurposed to pull back the heavy sled after each competitor's run. This keeps the contest moving smoothly and pays tribute to the engine's rugged, hard-working history in logging. The Stanley Steamer engine and axle 1939 Packard 120 steam conversion represents a fascinating blend of early 20th century automotive innovation and classic American styling. Originally a gasoline-powered luxury sedan, the 1939 Packard 120 was retrofitted with a Stanley steamer power plant, one of the most renowned steam engines in automotive history. The conversion involved installing a steam boiler, burner system, and the distinctive Stanley direct drive axle, replacing the conventional drivetrain. This marriage of Packard's elegant bodywork and the smooth, silent operation of steam created a unique vehicle that stood apart from its contemporaries. Unlike internal combustion, the steam system offered nearly vibration-free performance with impressive torque. Today, such a conversion highlights both the ingenuity of custom builders and the enduring fascination with steam power in the automotive world. The Armstrong Siddeley AS2 diesel engine, a rugged, two-cylinder power unit of the mid-20th century, found practical use in many remote corners of the world. In New Zealand, one such engine was employed to drive a 15x9 Colette and Son double-toggle stone crusher, an essential tool for breaking down river rock and hard local stone into usable aggregate. The AS2, with its steady thumping beat and reputation for reliability, was well suited to this hard labor. Once coupled to the crusher by heavy flat belts, it worked tirelessly through the day, turning the eccentric shaft that powered the crushing jaws. Each stroke reduced boulders to graded metal, destined for roadworks and farm tracks. Dust rose, belts hummed, and the diesel's slow, rhythmic exhaust marked the passage of steady progress. For its operators, this simple setup represented dependable productivity, a day's honest work powered by proven British engineering. Running today are some fine examples from the Choreboy line of engines produced between 1910 and 1924 before being uprated into the Iowa Oversize series. Each engine represents a different stage in the evolution of small stationary power, and together they form a living display of early 20th century engineering. The smallest of the lineup is the 1916 Choreboy 1 3/4 horsepower, a compact unit that offered reliable power for light farm and workshop duties. Next comes the 1915 Hired Man air-cooled 2 1/4 horsepower, notable for its air cooling system, making it especially practical in areas where water for cooling was not readily available. The 1916 3 Mule Team 3 horsepower demonstrates a step up in capability, designed to handle heavier chores with ease. Moving further along, the 1913 Farmhand 4 horsepower is one of the older models here, providing steady power for medium-scale farm work. Alongside it, the 1916 4 Mule Team 4 horsepower shows how refinements in design kept pace with the growing demand for efficiency. Completing the set is the impressive 1918 6 Mule Team 6 horsepower, a powerful machine that could take on the toughest agricultural jobs of its day. All of these engines are fitted with low-tension magnetos and igniters, giving dependable ignition under varying conditions. The outdoor models are hit-and-miss petrol engines mounted on their original factory carts, while the indoor example is throttle-governed, starting on petrol and switching to paraffin for economical running. Together, they bring to life the ingenuity and practicality of early farm power. The 1913 Air Motor 8 cycle was a rugged and practical engine produced by the Air Motor Windmill Company of Chicago, Illinois, a firm best known for its windmills. This particular model was designed to take over the job of water pumping when wind power was unavailable, making it a vital machine for farms and rural homesteads in the early 20th century. Unlike many high-speed engines of the time, the air motor 8-cycle was built to run at a very slow pace. This slow operation meant it could drive a pump directly, without the need for additional gearing. A large gear mounted at the front allowed the engine to be connected easily to pump mechanisms, and its design included 3-stroke adjustment holes, giving flexibility for different pumping needs. Farmers could adapt it to run either a pump jack or a deep well pump, depending on their water source. The engine was also valued for its simplicity and reliability. With its small petrol tank, along with oilers and greasers to keep it running smoothly, it required little oversight once started. Owners could set the machine in motion and leave it to complete the task of pumping water unattended. Durable, dependable, and straightforward, the 1913 Air Motor 8-cycle embodied the practical engineering that powered rural America. The Hinrichi hot air engine of 1899, rated at 1/60th of a horsepower, is a fascinating example of late 19th century engineering ingenuity. Hot air engines, also known as Stirling or caloric engines, were designed to operate on the principle of external combustion, making them safer and quieter alternatives to steam engines for small-scale applications. The Hinrichi Company, based in Germany, became renowned for producing finely crafted models that demonstrated efficiency and reliability for their size. The 1/60th of a horsepower engine from 1899 is a particularly delicate and precise machine. With its cast iron frame, polished brass fittings, and flywheel-driven design, it embodied the craftsmanship of the era. Despite its very modest power output, just enough to run small laboratory devices, demonstration equipment, or educational displays, it served as an effective teaching tool and an object of scientific curiosity. Unlike steam engines, the Hinrichi hot air engine required no boiler or high-pressure steam, greatly reducing risk of explosion. Instead, it operated by heating and cooling a working gas, usually air, which expanded and contracted to drive the piston. This slow, steady cycle gave it remarkable reliability, though at the expense of power and speed. Today, surviving Hinrichi hot air engines are rare and highly sought after by collectors of antique scientific instruments and model engineers. The 1899 and a 60th horsepower version represents not just a mechanical artifact but also an important step in the exploration of alternative engine technologies during the industrial age. The 1925 IHC McCormick-Deering 1.5 horsepower M is one of the most iconic small stationary engines of the early 20th century. Built by International Harvester Company, IHC, the Model M was introduced in 1917 and quickly became a favorite on farms and in small businesses due to its simplicity, reliability, and versatility. The 1.5 horsepower version was the smallest in the M lineup, designed to power light-duty applications such as water pumps, cream separators, feed grinders, and small generators. The engine was a hit-and-miss design, meaning it only fired when necessary to maintain speed, which conserved fuel and reduced wear. Operating on kerosene or gasoline, it was water-cooled with a hopper system and featured a robust cast-iron flywheel. Its simple mechanical governor and open crankcase made it easy to operate and repair, which was vital for rural owners who often had limited access to machine shops. International Harvester marketed the McCormick-Deering line as rugged and dependable, and the 1.5 horsepower M lived up to that reputation. Thousands were produced through the 1920s and beyond, and many are still in running condition today, a testament to their durability. Collectors value these engines not only for their engineering, but also for the role they played in easing labor on small farms during a transitional period in American agriculture. The 1925 McCormick-Deering 1.5 horsepower M remains a sought-after piece of machinery, embodying the ingenuity and practicality of early farm power equipment. The 1939 Lister Jr. A23 3.5 horsepower stationary engine is a fine example of British engineering from the golden age of small agricultural and industrial power units. Built by R.A. Lister and Company of Dursley, Gloucestershire, the Junior series was introduced in the 1920s as a lightweight, efficient solution for farms, workshops, and light industry. The A23 model, producing around 3.5 horsepower, was particularly popular for driving equipment such as pumps, generators, saw benches, and milling machines. Its compact design, simple operation, and robust construction earned it a reputation for reliability and longevity, with many units still in use or preserved today. This 1939 example is mounted on an original Lister trolley, which enhances both its functionality and historical appeal. The trolley was a standard option supplied by Lister, allowing the engine to be moved easily between jobs, making it especially valuable in agricultural settings where versatility was essential. Retaining its original trolley also adds to the authenticity and collector's value of the machine. The Junior engines were noted for their slow running characteristics, producing steady and reliable power with minimal maintenance. With distinctive flywheels and traditional hand-start operation, they embody the charm of pre-war engineering. Today, a Lister Junior A23 on its original trolley represents not just a piece of mechanical history, but also a tangible link to the working life of rural Britain in the late 1930s. The Armstrong Siddeley AS1 was one of the early post-war British gas turbine engines developed during the pioneering years of jet propulsion. Produced by Armstrong Siddeley, a company renowned for its aero engines and luxury cars, the AS1 represented an important step in the transition from piston-driven to jet-powered aircraft in the late 1940s. It was primarily designed as a small turbojet for light aircraft, research platforms, and experimental projects, reflecting the industry's efforts to explore new propulsion technologies outside of frontline military fighters and bombers. The AS1 featured a straightforward centrifugal flow compressor layout, a common design choice in the early jet age because of its mechanical simplicity and ease of production. This made the engine relatively compact and reliable, though less efficient at high speeds compared to later axial flow engines. It delivered modest thrust, suitable for lightweight applications, and provided engineers with valuable test data on materials, airflow, and combustion processes.
Shut this door.
While it never entered large-scale production or powered any major operational aircraft, the AS1 played a useful role as a development engine. Projects like the AS1 contributed significantly to Britain's accumulation of knowledge in turbine technology, helping to refine design practices and manufacturing techniques. In this sense, the Armstrong Siddeley AS1 can be seen as an important building block in the evolution of more advanced Armstrong Siddeley engines that would later serve in both military and civil aviation. The Pratt and Whitney R4360 Wasp Major stands as the ultimate expression of piston engine power in aviation history. Developed during World War II and entering service in the late 1940s, it was a breathtakingly complex machine, a 28-cylinder, 4-row, air-cooled radial engine with a displacement of 362 cubic inches. Arranged in a unique corncob layout, 7 cylinders per row stacked in 4 staggered rows, the R4360 represented the pinnacle of radial engine design, squeezing as much horsepower as possible out of the piston era. Producing an astonishing 3 500 horsepower in its most common configurations, and up to 4 300 in later versions. The Wasp Major relied on supercharging to maintain power at altitude, making it ideal for large, heavy aircraft. Its sheer size and output enabled America's biggest post-war airplanes to take flight, including the Boeing B-50 bomber, the Convair B-36 Peacemaker, and the Douglas C-124 Globemaster II. It also powered record-setting racers and experimental prototypes, bridging the gap between piston-driven aviation and the jet age. But such power came at a price. The R4360 was notoriously complex, with immense cooling challenges, high maintenance demands, and voracious fuel consumption. Mechanics nicknamed it corncob, with equal parts affection and frustration. Still, no other piston engine matched its brute force and engineering audacity. By the mid-1950s, jets rapidly eclipsed piston power, but the Wasp Major remains a mechanical marvel, a towering monument to human ingenuity and the final thunderous roar of the piston engine era. This unique 2086cc 7-cylinder radial engine is a remarkable example of engineering creativity built largely from air-cooled Volkswagen components. At its core, the engine repurposes parts from the classic VW Beetle 1200, though most of them have been carefully modified to fit the radial configuration. The cylinders, pistons, and cylinder heads all trace their origin to Volkswagen, as do the pushrods, bearings, valve train, oil pump, and starter. These familiar elements provide a solid and proven foundation, ensuring reliability while allowing for the performance and layout demands of a radial design. To bring the engine into the modern age, electronic ignition has been incorporated, ensuring consistent spark delivery across all 7 cylinders. Fuel delivery is handled by an electric fuel pump, while breathing is optimized with a double Solex carburetor setup featuring twin 40mm barrels. This combination provides both the airflow and the precision needed to keep the unusual radial arrangement running smoothly and efficiently. What makes the project especially impressive is that all other required parts, the ones not salvaged or adapted from Volkswagen, were crafted entirely by hand. From custom housings to specialized fittings, each non-VW component has been designed and manufactured to harmonize with the Beetle parts while maintaining the geometry and balance demanded by a 7-cylinder radial engine. The result is a highly customized, one-of-a-kind power plant that bridges classic automotive engineering with the ingenuity of home-built craftsmanship. The completed engine not only demonstrates the versatility of Volkswagen's air-cooled design, but also showcases the determination and skill required to adapt automotive parts for an aviation-style radial configuration. With its 2086cc displacement, unique 7-cylinder rhythm, and blend of factory and homemade components, it stands as both a technical achievement and a celebration of mechanical creativity. This 350 horsepower Fairbanks-Morse engine, built in 1942, is a striking example of mid-20th industrial power. With a 14 inches by 17 inches bore and stroke, it was designed for strength and reliability, starting on compressed air rather than electric ignition. For more than 4 decades, until 1985, it generated electricity, serving as a dependable workhorse in its era. Visitors can still experience its raw mechanical presence today, hearing the deep, rhythmic thrum as it comes to life, and watching a connecting rod in motion through a viewing window into the crankcase, offering a rare glimpse inside a living machine. In 1940, during the German occupation of Denmark, the Wehrmacht installed a powerful Deutz Humboldt diesel engine at the fortified island of Flakfortet, situated in the Orson Strait outside Copenhagen. The island, originally constructed as a coastal defense fort, was taken over by the occupying forces and transformed into a military stronghold. Reliable electricity was essential for operating the fortress, powering searchlights, communication systems, and other military equipment. The Deutz diesel was brought in specifically to serve this purpose, providing a steady and dependable source of power under demanding wartime conditions. After the war, the engine, along with several large Burmeister and Wain B&W motors dating back to 1914, remained on the island. Over the decades, these machines were left exposed to the harsh sea air and the ravages of time. For 60 years, they stood unused, slowly decaying under layers of rust. Vandals stripped parts, and the valuable copper components were stolen, leaving the once proud machinery in a state of ruin. Eventually, the Engine Collection, an organization dedicated to preserving industrial heritage, undertook the ambitious task of salvaging these historic engines. The Deutz diesel, together with the old B&W motors, was transported from Flakfortet to their facilities. Restoring them to working order required painstaking effort. Every surface had to be cleaned of corrosion, missing parts were rebuilt or fabricated, and vital systems had to be reconstructed from scratch. Despite the immense challenges, the engine collection succeeded in bringing these remarkable machines back to life. What had once been abandoned relics of war and neglect were transformed into fully functioning examples of early 20th century engineering. Today, the restored Deutz Klockner-Humboldt diesel and the century-old B and W engines stand not only as reminders of wartime history, but also as testaments to the resilience of industrial craftsmanship and the dedication of those who preserve it for future generations. The Deutz MA 218 engine is a classic marine diesel engine that represents the robust engineering and reliability for which Deutz has long been recognized. Designed specifically for ship propulsion and auxiliary duties, the MA 218 was widely used in the mid-20th century, particularly in coastal vessels, fishing boats, and small to medium cargo ships. Its design reflects the emphasis on durability, fuel efficiency, and ease of maintenance, critical factors for marine operators working in often challenging environments. The MA 218 is a 4-stroke medium-speed diesel engine built with a focus on simplicity and solid mechanical construction. It features direct fuel injection, ensuring efficient combustion and dependable performance. Like many Deutz engines of its era, it was air-cooled, which reduced reliance on seawater cooling systems and made it particularly suitable for regions where water quality posed challenges. The air-cooled design also reduced corrosion issues commonly associated with saltwater use. Known for its longevity, the MA 218 could run for extended periods with minimal intervention, provided it was properly maintained. Spare parts availability and straightforward mechanical systems meant that ship crews could often carry out routine servicing and minor repairs themselves. Although newer, more advanced engines have since replaced it, the Deutz MA 218 remains respected as a reliable workhorse of marine diesel history, remembered for its ruggedness and steady performance at sea. The Auglaize engine in Pat's Morning Lace is portrayed as a subtle yet powerful presence, quietly driving the rhythm of the narrative. More than a mechanical device, it symbolizes the blend of tradition and innovation that underpins Pat's world. Its polished casing and intricate gears mirror the delicate patterns of lace, suggesting that technology and artistry can weave together seamlessly. The engine doesn't roar but hums with a steady, almost musical cadence, echoing the calm persistence of morning routines. Within the story, it becomes both a practical tool and a metaphor, propelling progress while preserving the gentleness of handmade craft. The Auglaize engine embodies harmony between the industrial and the intimate, reflecting Pat's balance of discipline and quiet creativity. The Allison 1710 V12 engine was a liquid-cooled 12-cylinder aircraft power plant developed in the United States before and during World War II. Displacing 710 cubic inches, it delivered between 750 and over 1 600 horsepower, depending on the model and supercharging system. Designed for reliability and ease of production, the V-1710 powered many iconic aircraft, including the Lockheed P-38 Lightning, Bell P-39 Era Cobra, Curtiss P-40 Warhawk, and early North American P-51 Mustangs. Unlike some contemporaries, it often lacked a two-stage supercharger, limiting high-altitude performance in certain fighters. Nevertheless, the Allison engine earned a reputation for toughness, smooth operation, and adaptability, making it a cornerstone of U.S. aviation power plants throughout the war. The Armstrong Siddeley AS1 single-cylinder diesel engine was an early experimental power plant developed in the 1930s, during a period when manufacturers were exploring compact compression ignition engines for both automotive and industrial applications. Armstrong Siddeley, best known for its luxury cars and aero engines, sought to diversify into small diesels as demand for efficient, durable engines grew in agriculture, light vehicles, and stationary machinery. The AS1 was a simple, robust design, featuring a single vertical cylinder with direct fuel injection and water cooling. Its displacement was modest, producing only a few horsepower, but it was built to demonstrate the principles of diesel operation on a compact scale. Unlike multi-cylinder diesels of the time, which were expensive and mechanically complex, the AS1 aimed to deliver reliability and low fuel consumption in a relatively affordable package. The engine incorporated heavy cast-iron construction for durability, with a low-speed operating range suited to tasks such as pumping, generators, and light industrial equipment. Although not widely adopted in commercial vehicles, it served as a testbed for Armstrong Siddeley's engineering work on diesel combustion and fuel injection systems. While Armstrong Siddeley's reputation ultimately rested more on their advanced aero engines and luxury cars, the AS1 highlights the company's experimental ventures into small diesel technology. Though it never achieved mass production or broad market success, the AS1 stands as an interesting example of early British diesel engineering, reflecting both the technical curiosity and practical limitations of the interwar period. The Armstrong Siddeley AS2 was a compact two-cylinder opposed-piston diesel engine developed in Britain during the mid-20th century. Designed by Armstrong Siddeley Motors, a company well known for its aero engines and luxury cars, the AS2 was part of a family of lightweight diesel engines created for small vehicles, industrial equipment, and auxiliary power units. Its development reflected the increasing interest in economical and durable diesel technology during the interwar and post-war periods, particularly for military and utility applications, where reliability and fuel efficiency were essential. The AS2 featured two horizontally opposed cylinders, air-cooled for simplicity and reduced weight. Its displacement was modest, but the engine was notable for delivering excellent fuel economy and a high degree of mechanical robustness compared to contemporary petrol engines of similar size. One of its key advantages was its ability to operate on a variety of low-grade fuels, which made it attractive for use in regions where fuel quality was inconsistent. Applications of the AS2 included light vehicles, small boats, agricultural machinery, and generator sets. The engine's twin-cylinder layout kept vibration levels relatively low, while its simple design made it straightforward to maintain in the field. Its rugged build and long service life earned it a solid reputation, especially in demanding environments. Although Armstrong Siddeley is more famous for its aero engines such as the Cheetah and Sapphire, the AS2 highlighted the company's versatility and willingness to experiment with compact diesel designs. It contributed to the growing adoption of diesel technology in sectors beyond heavy trucks and locomotives. Today, the AS2 is remembered as a niche but significant product of Armstrong Siddeley's engineering legacy, illustrating the brand's commitment to innovation across a wide range of power applications. The Petter AVA2 diesel stationary engine, introduced in the late 1950s, is a fine example of British engineering designed for durability and dependable service in agricultural, industrial, and remote applications. Manufactured by Petter Limited, a company based in Yeovil, England, the AVA2 was part of the wider AVA range, which was well regarded for its rugged simplicity and fuel efficiency. The 2 in AVA2 denotes that this model is a two-cylinder version, providing more power and smoother operation compared to single-cylinder variants. The AVA2 was produced in 1958 at a time when stationary engines were indispensable in powering equipment, such as water pumps, generators, small machinery, and even agricultural threshers. Its air-cooled, diesel-fueled design made it economical to run and easy to maintain, even in challenging conditions where water cooling systems might not be practical. The compression-ignition diesel system gave it a reputation for reliability and longevity, which meant many units remained in use for decades after manufacture. Built with a cast-iron body and a straightforward mechanical layout, the AVA2 was engineered for ease of servicing. Parts such as fuel injectors, filters, and lubrication systems were designed to be accessible, ensuring minimal downtime. Its relatively low-speed operation, combined with a heavy flywheel, ensured smooth and consistent power delivery, qualities essential for steady operation of connected equipment. The Petter AVA2 also became popular for its adaptability. Farmers and engineers valued it for its ability to run day after day, with little more than basic maintenance. Even today, vintage engine enthusiasts seek out the AVA2 as a collectible piece of machinery, restoring and exhibiting it at rallies. The 1958 Petter AVA2 remains a testament to mid-20th century British diesel engineering, embodying reliability, practicality, and robust design. The idea of a jet turbine garden tractor engine is both unconventional and fascinating. Instead of relying on a traditional gasoline-powered piston engine, this concept involves integrating a small-scale jet turbine, essentially a miniature version of those used in aircraft, into a tractor designed for lawn and garden work. Jet turbines operate on the principle of drawing in air, compressing it, mixing it with fuel, and igniting the mixture to produce thrust or rotational power. In a tractor application, the turbine would not be used to push the vehicle with raw thrust. Instead, it would be geared to drive a shaft, powering the wheels and implements. One of the most notable advantages of a turbine-powered garden tractor is its power-to-weight ratio. Turbines can produce a remarkable amount of power relative to their size and weight, making the machine both compact and potentially overpowered for its intended tasks. Additionally, turbines have fewer moving parts compared to piston engines, which can mean smoother operation and less mechanical wear over time. The distinctive high-pitched whine and flame-spitting exhaust also add a dramatic flair, turning ordinary yard work into something resembling a jet show. However, the practical challenges are significant. Turbines are inherently fuel-hungry, especially at low power levels, which makes them far less efficient than conventional engines for slow-speed tasks like mowing or tilling. They also generate extreme heat, raising concerns about safety in a residential setting. Maintenance and operating costs would be considerably higher, given the specialized nature of turbine components. In reality, turbine-powered tractors remain more of a novelty or experimental engineering project than a viable commercial product. Hobbyists and enthusiasts occasionally build them for exhibitions or competitions, showcasing the fusion of aerospace technology with everyday machinery. While impractical for most homeowners, the concept highlights human creativity in reimagining even the most ordinary tools with extraordinary engineering.
Never drive it, huh?
An articulating cylinder two-stroke putt-putt motor is a unique variation of the classic toy boat engine, where the cylinder itself pivots or articulates rather than remaining fixed. Like traditional putt-putt engines, it operates on the principle of heating and cooling water to create steam pulses that drive a simple piston or diaphragm. The articulating design improves efficiency by reducing friction and allowing smoother reciprocation within the small motor. As steam expands and contracts, the cylinder rocks back and forth, producing the characteristic putt-putt sound while propelling the boat. It's a clever, low-tech demonstration of thermodynamics and mechanics. In 1934, Deutz, one of the world's oldest engine manufacturers, produced several notable stationary diesel engines, including the MIH 322. This model exemplified the company's engineering focus during the interwar period, when reliability and efficiency were paramount for industrial applications. The Deutz MIH 322 was a medium-sized, single-cylinder stationary diesel engine, widely used for powering generators, pumps, mills, and other equipment in rural and industrial settings where electrical grids were not yet common. V. A distinguishing feature of the MIH 322 was its air start system, a technology used to initiate combustion in large diesel engines. Instead of relying on electric starters, compressed air was introduced into the cylinder to drive the piston and bring the engine up to firing speed. This system proved especially effective for robust stationary units, where reliability in harsh conditions was more important than convenience. As a stationary diesel engine, the MIH 322 embodied the rugged characteristics of Deutz's early designs: heavy cast iron construction, efficient fuel consumption, and the ability to operate continuously for long periods with minimal maintenance. Engines like the MIH 322 played a vital role in mechanizing agriculture and industry during the 1930s, bridging the gap between manual labor and the widespread adoption of electrification. The Deutz MAH 914 is a single-cylinder, four-stroke diesel engine produced in the early 1950s by KHD Deutz AG, a German manufacturer well known for its robust air-cooled engines. The 1951 model was part of the MAH series, which became popular in agriculture and small-scale industry due to their durability and simplicity. The MAH 914 was designed as a stationary engine, primarily used for driving equipment such as threshing machines, water pumps, small generators, and other farm machinery. It featured direct fuel injection, which was advanced for its time, ensuring efficient combustion and reliable performance even under heavy workloads. With a displacement of around 1.4 liters and an output of roughly 10 to 12 horsepower at low RPMs, it was ideal for continuous operation, often running for long hours without significant wear. A key advantage of the engine was its air cooling system, eliminating the need for water radiators and reducing maintenance. This made it particularly well suited for rural areas where water supply and service facilities were limited. Known for its slow, rhythmic exhaust note and long lifespan, the Deutz MAH 914 of 1951 remains a valued piece among vintage machinery collectors and still demonstrates the ingenuity of post-war German engineering. The Deutz stationary engine is a classic example of robust German engineering, designed for reliability and long-term performance in industrial and agricultural applications. Manufactured by Deutz AG, one of the world's oldest engine makers, founded in 1864 by Nicholas Otto, these engines played a significant role in powering machinery before the widespread use of electricity and modern diesel systems. Stationary engines from Deutz were widely used to drive equipment such as pumps, sawmills, threshers, generators, and compressors. Known for their air-cooled design, many Deutz engines eliminated the need for complex water cooling systems, making them easier to maintain in remote areas. Their reputation for durability came from a solid cast iron build, simple mechanics, and efficient fuel use. During the late 19th and early 20th centuries, Deutz stationary engines helped mechanize farming and small industries, providing dependable power where human or animal labor was insufficient. Today, vintage Deutz stationary engines are prized by collectors and enthusiasts, often restored and displayed at engine shows. They stand as a testament to early internal combustion innovation and the engineering vision of Nicholas Otto, whose work laid the foundation for modern four-stroke engines. The rotary valve Crossley engine at the Cool Spring Power Museum is a rare and historically significant example of early internal combustion innovation. Built by Crossley brothers of Manchester, England, pioneers in gas engine design, the engine departs from the more common poppet valve arrangement by employing a rotary valve system. This design was intended to simplify valve motion, reduce wear, and improve efficiency by providing smoother gas flow into and out of the cylinder. At Cool Spring, the preserved rotary valve Crossley stands as both a technical curiosity and a testament to the experimental spirit of late 19th and early 20th century engineering. The rotary valves ultimately proved less practical in heavy-duty service due to sealing and lubrication challenges. The engine demonstrates the bold efforts made to refine power generation during a period of rapid industrial progress. Today, it remains a highlight for enthusiasts who visit Cool Spring to witness the evolution of gas engine technology. A 2 HP domestic mud pump engine is a compact and efficient machine designed for pumping muddy water, slurry, or water mixed with debris in households, small farms, and construction sites. Powered by a 2 horsepower engine, it delivers reliable suction and discharge performance, making it suitable for applications such as dewatering pits, draining flooded areas, or supplying water from ponds and wells. These pumps are usually lightweight, portable, and easy to operate, ensuring convenience for domestic users. Constructed with durable materials, the pump can handle abrasive particles present in muddy water without frequent wear. Many models come with a self-priming feature, which saves time and effort in operation. Its low fuel consumption and minimal maintenance needs make it cost-effective for daily use. Overall, a 2 HP domestic mud pump engine provides an ideal balance of performance, efficiency, and durability for households and small-scale water management tasks. The rotary Gnome 9 engine, formerly known as the Gnome 9 monosoupape, was a groundbreaking aircraft power plant developed in France during the early 20th century. Introduced in 1913 by the Société des Moteurs Gnome, it quickly became one of the most widely used rotary engines in aviation during the First World War. The engine featured 9 cylinders arranged radially, with the entire cylinder block and crankcase rotating around a fixed crankshaft. This rotary configuration provided excellent cooling and allowed for high power-to-weight efficiency, a crucial advantage for early fighter and reconnaissance aircraft. The Gnome 9 produced around 100 horsepower, a remarkable output for its time. Its most innovative feature was the monosoupape single-valve system, which eliminated the need for traditional intake valves. Instead, fuel-air mixture entered the cylinder through piston ports, simplifying the design and reducing weight. While this innovation increased reliability, it also introduced limitations in throttle control. Pilots could not finely regulate engine power. Instead, they often had to blip the ignition on and off to adjust thrust, making flying more challenging. Despite these drawbacks, the Gnome 9 powered many iconic aircraft, including the Nieuport, Sopwith Pup, and early versions of the Sopwith Camel. Its lightness and relatively smooth operation made it a favorite among aviators, though the high gyroscopic forces of its spinning mass influenced flight handling significantly. By the end of the war, rotary engines like the Gnome 9 were gradually replaced by more efficient inline and radial engines, but its role in shaping early aviation technology remains historic and influential.